Hi all. In this lecture, we're going to continue the discussion on the convergence of the Fourier transform. And once we're done with that, we will discuss some basic partial differential equations, starting with the diffusion equation, and introduce something you already have seen in your undergraduate courses, mathematics, mainly the method of separation of variables for solving some fundamental PDEs to scientific and engineering applications. All right, so let's go back to discuss a little bit about the Fourier expansion and some of the convergence properties. So I remind you, we represented a periodic function f with the Fourier series that you see in the equation on the top. And I remind you here the function f had a period 2L. You can easily see here if you put x plus 2L, right? This is a periodic function with a period 2L. And the coefficients that you see were computed directly from the function f of x by using the so-called Euler formulas that you see in the equations on the middle of this slide. So we haven't really said very much here beyond the fact that we start with a function f of x that is periodic. And I'm assuming also the function here it's integrable in the interval from minus L to L. But with all that, we just computed the coefficients AM and BM, plug them in this expansion, and that's the Fourier representation. So what we would like to know is, given the series expansion, does it converge to the function f of x for every x? And do we require any other constraints on the function f of x? So we will review this shortly with one theorem, but before that, let me just give you sort of a brief reminder of what we already have seen before, which is functions that are piecewise continuous. So we have seen this in earlier lecture on ODEs. So what I have in the schematic is a function defined in the interval a to b. You can see it's defined in pieces, and in every piece, the function is continuous. Now, formally, the definition of piecewise continuous function also requires some constraints on the limits of the function at the ends of every interval. So if I look at this central interval, basically these conditions 2 and 3, they say that as I approach this point here from the right, the limit of the function should be finite, and similarly as I approach this point from the left, the limit of the function should also be finite. So if we have these properties 1, 2, and 3 satisfied, then we call this function f of x to be piecewise continuous. So for these functions, if we have a discontinuity like you see at this point, you can define the values of the function on the right and the value of the function on the left. So this would be becoming useful when we use the Fourier transform and we try to see what exactly it gives us at points of discontinuity. Okay, so let me just give you directly the theorem. So we are going to assume that the functions f that we're dealing with plus their first derivative f prime are piecewise continuous on the interval minus L to L. We're obviously going to assume that the function f is periodic in the interval minus L to L, so we have a period of 2L. So then we can represent the function with a Fourier expansion the way that you see here, with the coefficients computed with the Euler formulas. And the theorem says that this expansion converges to all points where the function is continuous, it converges to f of x, and in the points where f is discontinuous, it converges to 1/2 of x plus f of x minus. So if you average the values of the function f from the left and the right, then the series will converge to that average. So in many applications, when you have to write a Fourier expansion of a function, you're not going to be told what the values of the function are going to be at the edges where you have discontinuities. But here, if you're going to use the Fourier expansion, the theorem says that at the points of discontinuities of the function f, this series expansion converges to the value that you see in here, the average of the values on the left and the value of the function on the right. Now, the conditions that we have seen in this theorem, they are sufficient, and actually they're not the most general sufficient conditions you can have, but certainly they are not necessary. So effectively, the type of functions the theorem doesn't cover are functions that have infinite discontinuities in these pieces where the functions is defined as in a continuous manner. So, for example, functions like 1 over x squared, we will not be able to do a Fourier expansion in the interval, let's say, minus L to L. Now, interestingly enough, when you have a Fourier expansion, you can look at all the terms in the Fourier expansion, let's say sines and cosines, and they may give you the impression, because you can differentiate sines and cosines as many times as you want, you may get the wrong impression that this Fourier series converges to a function that is differentiable to any order you want to, since you can do this with a Fourier expansion. However, note that the Fourier expansion may converge to the function that is not differentiable or continuous. Okay, so even though every term looks to be differentiable and infinitely, in principle, differentiable, the series itself may converge to the function that is not differentiable. So we're going to consider one example, and the example is the square wave. So we're going to take a function. Let me just give you the schematic. We're going to take this function that is periodic with a period 2L. So in the interval from minus L to 0 is equal to 0, takes the value L from in the interval 0 to L. No particular reason why the interval setting and the value of the function are the same, just to make life easy. And you notice there is no indication here what the value of the function is, let's say at x equals 0, or at x equal L, or at x equal minus L. So obviously we do anticipate that if we do a Fourier expansion, somehow we will have a series, we will obtain a series that at this point of discontinuities, let's say, for example, at x equal to 0, it will converge to the average of the value L and the value 0, so it will converge, it will give us basically L over 2. Okay, so we will see this in the following slide. We're going to take a function. Let me just give you the schematic. We're going to take this function that is periodic with a period 2L. So in the interval from minus L to 0 is equal to 0, takes the value L from in the interval 0 to L. No particular reason why the interval setting and the value of the function are the same, just to make life easy. And you notice there is no indication here what the value of the function is, let's say at x equals 0, or at x equal L, or at x equal minus L. So obviously we do anticipate that if we do a Fourier expansion, somehow we will have a series, we will obtain a series that at this point of discontinuities, let's say, for example, at x equal to 0, it will converge to the average of the value L and the value 0, so it will converge, it will give us basically L over 2. Okay, so we will see this in the following slide.
Is 1/2 of the values on the left and the right of that point, which is L and 0, so this is matches with what the theorem says. All right, let me jump now to slide 62. Okay, and discuss a little bit about even and odd functions. So first, the definition of an even function. So if we look at a certain interval, so basically the definition is f of minus x should be equal to f of x for each x in that interval. Okay? Again, f of minus x equal to f of x, and you can see here one example where this particular function takes the same value for x and minus x. An odd function is a function where f of minus x equals minus f of x, and you can see here, if you take f at a given value of x, is minus f at minus x. And because this has to be true for every x in the interval, if you plug in x equal to 0, the only way that this is, can be satisfied is f of 0 equal to 0. Can you see that? So in those cases, we really, I mean, to call this an odd function, we really have to specify the value of f at that point, and you notice that dot there says f of 0 equal to 0. Okay, that is important. All right, so why do we care about even and odd functions? Because you will see from, or you can guess from the Fourier series expansions that maybe the sines will drop out, or maybe the cosines will drop out. So let's actually look at slide 65 on a cosine series. And so let's take a function that's an even function. All right, so we're doing a Fourier series expansion of something that is an even function. So remember the coefficients Bn. The coefficients Bn are 1 over L, integral from minus L to L of f of x times the sines. Now, if f of x is an even function, what function are the sines? Are the sine function odd? Odd, right? So even times odd, what do you get, do you think? If f is even, f times the sines, what type of function do you get? Odd, okay? So if you get odd, it will be, when you do the integral, half of it, in the domain, the function will be plus, the other half minus, so you will actually get 0. So the b's are 0. And the only thing you get for an even function is the coefficients an that involve these cosines. So the expansion looks like that. So an even function has a cosine series expansion. Very convenient. So when you see an even function, you don't have to go and calculate the sine terms. You can just directly write this expansion here with only the coefficients an computed the way that you see here. So this is known as the Fourier cosine series. And obviously, if you have an odd function, the opposite is going to happen. The coefficients an that multiply f with the cosines will drop, and you stay only with the bn's. And that's the Fourier sine expansion. In general, of course, if you have some arbitrary function, you're going to have both the cosines and the sines, all right? And so you have to compute both of them. OK, so let me introduce, I'm going to pass a few slides, but I'm going to summarize everything they include with one slide only. So I'm going to consider actually, let me just, this is what I need. So let's take this function f of x. Don't look in the picture yet, right? Let me take this function f of x that is 1 minus x from 0 to 1. So from 0 to 1 is this line that goes from 1 to 0 that you see here. And then from between 1 and 2 is equal to 0. I don't give you anything else, right? So you don't have this picture that you see there. So this is my function. And you would like to use, a Fourier expansion for this function, right? So the first thing you need to do is you need sort of to produce some periodic version of this. And then once you're done with that, you say, I'm going to concentrate and use that Fourier expansion only from 0 to 2. And hopefully, right, obviously, it will represent, basically, it will be a Fourier series expansion of this function in that interval. You understand? So you don't need to have, you make something periodic to apply Fourier series expansion, but the bottom line is, when you look at this function, you only care what's going on between 0 and 2. So once you have your Fourier series, now you say this will converge in the interval 0 to 2 in this function, and that's what you care, right? Yep? Yes, thank you. All right, so the question is, how do you make it a periodic function? And there are two ways. One of the ways is this picture that you see here. So before you see any equations and any statements, can you look at this picture and tell me what did I do to take this function and make it a periodic function? Look at the picture and tell me what did I do to make it a periodic function? Just from the picture alone. So obviously the interval here, my L is 2, so the periodic function is defined in one period between -2 and 2, all right? So what have I done to this function to make it periodic? I mean, I did something first in this interval, and then, of course, it's repeated. But what have I done in this interval? What have I done between -2 and 0? But be precise mathematically. An even extension of the function. So what we have done is we basically took, indeed, the mirror version of this with respect to the y-axis, but effectively, we have produced an even extension of this function f of x in the interval -2 to 2, all right? It's an even extension. And why I care about an even extension? Because here is another version of the same function that's an odd extension. Can you see that, right? I mean, f of minus x, right, is equal minus f of x. So if I'm really interested in the interval 0 to 2, but to be able to use the Fourier series expansions, I produced an even periodic extension of the function, the way that you see on the left picture. And on the right, you see I produce an odd periodic function. So the even periodic extension of the function f is going to have the cosine expansion. We have just seen it. This is going to have the sine expansion of what we have seen it. And you can use one or the two to actually have a Fourier representation of the function of interest in the interval of interest. And the bottom line here is, you know what? There is no such a thing as a unique representation in terms of Fourier representation of a function, because you can define different sort of periodic versions. All of them converge to the same function, but they look different. As a matter of fact, in the previous slide, it indicates actually that you can define sort of completely arbitrary extensions of functions. So for example, here, I took the function to be an even periodic extension of f, but you know what? Don't you think that from -2 to 0, I can do anything I want to? Is there any reason that I can do a periodic extension? Can I just use 0? Can I put a 0 value from -2 to 0? What do you think? Can I use anything? The answer is yes. All right? Now, why should I use an even expansion or an odd expansion is because you get cosines and sines only, and it makes the calculations easier. Okay, so this summarizes the discussion about Fourier expansions. One of the things that I haven't said anything yet, and it depends on if we're going to have time at the end of the semester, and if we don't, I may give it to you as a homework problem or an exam problem, is what is the error when you do a Fourier series expansion precisely? And more importantly, what happens is if you use an expansion where you keep 5 terms, all right, is not the same as using an expansion that you use 5 terms, but you have omitted, let's say, the 3rd term. If you're going to keep 5 terms and you want the best approximation with a Fourier series expansion, you need to use sequentially the terms n equal to 2, n equal to 3, n equal to 4, n equal to 5. So basically, the expansions that you get when you truncate them, they are optimal in a certain way. So when you truncate them at n and you keep all the terms, there is an optimality condition that you can easily solve for the expansion. As a matter of fact, you know exactly how much the error is going to be reduced when you keep one more term. So the expansion has very nice properties, basically. And so in textbooks, in mathematics, you will see convergence estimates of the expansion. So I may give you actually some of this for homework, but we will see. They're not very difficult, but I'm just, at present, I don't have time to cover those. Okay, so let me start moving to partial differential equations. So we can cover today the heat conduction equation. I'm assuming all of you have taken courses on PDEs on elementary level, so I am not doing anything fancy, anything advanced, or anything like that. I am doing PDEs 101. So I'm interested to model heat conduction on a bar, all right, that goes from 0 to L. And I'm assuming that the heat transfer that I'm trying to model is uniaxial, so the temperature U only depends on the location X, so there is no variability in Y and Z. So we only do the 1D problem. And so we will try to solve the heat conduction equation. I am not deriving it today, but it's in the notes. And the derivation is actually very simple. All right, so you should look at it. Okay, it's just the equation of heat conduction comes from balance of energy in an infinitesimal element of the road. So what I'm going to do is I am going to write down what the equation for 1D heat conduction is. Usually, I would not use an alpha square there. I would just use a simple alpha. You will not see alpha square in heat transfer books. But this alpha square, the way it is written here, is the conductivity divided by the density divided by the specific heat. Okay? So, and I think the only reason that there is an alpha square there is later on to see some similarities with the wave equation or some differences with the wave equation where we do get an alpha square there. But just keep in mind, right, we have an alpha square that is going to make the algebra a little bit simpler, but in literature, usually you have an alpha for the diffusivity. Okay, and the units for this diffusivity is length squared divided by time. Again, that's not the subject of interest to this course. So what I want to do is I want to put some initial conditions. And you can see I specify a function f of x to be my initial condition at time t0. And then I need to try to play with different type of boundary conditions. And for example, I can use boundary conditions that they're homogeneous. I can say at x equal to 0, my u is 0. At ul, this is equal to 0. And effectively, I want to solve the following boundary value problem. Now, I call this a boundary value problem, but actually somebody can argue that this is an initial value problem. And it is both, because it is, if you concentrate on ut and the initial conditions, right, it's an initial value problem. If you concentrate on the left-hand side, it is actually a boundary value problem, and you can see the boundary conditions at the two ends of the bar. As a matter of fact, the ideal way to see this problem is if you work in, if you treat space the same way you treat time, then you know what type of problem this is? It's a boundary value problem in space-time, right? So if you treat in one direction x, in the other one t, you can actually put boundary conditions on every side of that domain in the space-time, right? But usually in this course, we don't do those type of things, okay? Because you don't like mixing space and time, but there is a merit actually to look at these problems that way. So bottom line, it is an initial value problem because we have an initial temperature specified and we have the derivative ut, and it is a boundary value problem because we have this double derivative with respect to x, and we have this boundary, these 2 points with specified u. Now, these two boundary conditions are the simplest possible you can have, and this is what I'm going to start today, but obviously you can have way more complex boundary conditions, and we will maybe try to see one or two examples today. Okay, so let me see, this is slide 79. So let me jump to slide, if I'm correct, 81. Actually, it doesn't say anything, so let me go to slide 82. So this is what I need. So we're going to try to solve this, and we're going to introduce a method that I hope you have heard before. There is nothing sophisticated about it. The method is called separation of variables. Anybody heard this before in your classes? Right? Okay. So, so the idea here is we have a function of x and t. So we're going to split it. We're going to look for solutions that somehow are the products of two functions, one that is only a function of x, and another that's a function only of t. Okay? We don't really know that this will work. As a matter of fact, it only works for some differential equations. It works for the diffusion equation like this, for the wave equation, the Laplace equation. For other equations, this will not work. Okay? But it works nicely here, and we will see how the eigenfunctions and eigenvalues come in. So we are going to plug in this approximation. Obviously, we are looking for these functions. So we plug them in there. So we need second derivative of u. So we have x double prime times capital of t. And then we have u derivative of u with respect to t. So we're going to have x times t prime. So if you separate all the x's on the left and all the t's on the right, you conclude that the left-hand side is only a function of x, right? Because x is only a function of x. The right-hand side is only a function of t. So these two terms have to be constant, right? An equal constant. I mean, the same constant needs to prescribe both the left and the right-hand side. So let's call this constant minus lambda. Okay? So the equation for x becomes x double prime plus lambda x equal to 0. The equation for t becomes t prime plus alpha squared lambda t equal to 0. So you know what we have done is with a trivial, with this separation of variables, we took a partial differential equation, and now these two equations are what type of equations? When you look at them, what are they partial differential equations? Ordinary differential equations, right? So that's actually fantastic, right? And there is lots of other methods when you take a PD course that you will hear that they are more sophisticated, where the objective is to bring in ODEs in an attempt to solve PDs, but now we sit on a very simple case with separation of variables. All right, so we have to solve this, and obviously, before we solve these ODEs, we have to take care of boundary conditions. And so let's look at the boundary condition at x equal to 0. We said this homogeneous is equal to 0. So you remember the definition of u is capital X, capital T. So at x equal to 0, you get x of 0 times t of t equal to 0. Obviously, you're not going to go and say from this equation t of t is equal to 0, because then nothing is going on, right? Everything in time is 0. That doesn't look a good solution. So the solution will be to take x of 0 to be equal to 0. And similarly, if you apply that, you have x of L equal to 0, which is nice, because now the boundary value problem in little x becomes this differential equation, this ODE, with 0 conditions on the left and the right. And this equation, if you remember, we talked about it in the lecture on Monday, exactly this equation. You remember that? I mean, there was no capital X there. There was a Y, I think, but it was exactly the same equation. And what did we conclude on Monday for this equation with 0 values at the end? What did we conclude? You don't remember? Now, you don't have to remember numbers, because I don't remember numbers too, right? But what was the idea? That somehow this equation has solutions only for what? For specific values of lambda. And we call those, what did we call them? Those were the, say it. Yes, you can. The eigenvalues, right? The same way when you solve AX equal lambda x, that problem has a non-zero solution for specific lambdas that are the eigenvalues. So this has solutions only, non-zero solutions, right? Because you can see obviously the zero solution is a solution, but it's of no interest. So this has non-zero solutions for some specific values of lambda, and the corresponding capital of x are the eigenvectors of this two-point boundary value problem. So we did this on Monday, and here are the eigenfunctions. Can you remember those? Can somebody remind me from where we get this? Because I'm dizzy now. I just cannot think properly. Where did we get this from? Where did this thing come from? So we apply basically the one coefficient goes to 0, and then we apply the other boundary condition at x equal to L, right? And that gave us the eigenvalues, and whatever term sign we had there gave us these eigenfunctions. That's it. Okay? All right. So that's, and so the eigenvalues, the particular lambdas for this problem to have a solution are n squared pi squared over L squared for n equal 1, 2, 3. Okay? These are the eigenvalues. And then, you know, now that we have these eigenvalues, we can go back to the problem that involves capital T of little t. And, but the way you notice why we're using here an alpha squared versus alpha that people use in heat transfer books, because there is squares here. And so, you know, you can combine those squares with alpha and get something nicer. So you don't need to put square roots and all of this blah, blah, right? So you can get a nice thing. So will you agree with me if you solve this problem that you get this? Is that the solution? Does it look reasonable to you? So if you put lambda to be one of those, right, what do you get? In that ODE. Is that correct? Yes? Is that the solution of that ODE? I don't hear a thing. Yes. You know, one of the things I have to tell you, as a professor, that I deeply dislike is silence. I find it the most annoying thing to be teaching, sometimes for hours, to an audience that have no clue if they're interested in what I have to say, or, you know, or I waste their time. Silence is not good. Okay? It's not good, not just because I don't like it, it's not good for you too. Because, you know, if you don't say, no, this is right, this is wrong, how are you going to learn, you know, if you can only say what you think is right? You have to say things that you think are wrong, so you can go home and say, what a dumb thing I said, right? That's how you learn, okay? You need to have the guts to say the right and the wrong, and then identify, learn from positives and negatives. You don't learn only from positives, okay? All right, so this is the solution of this equation. And remember, when you integrate this, you get a constant of integration. So we have capital of X, capital of T. So we took care of the two boundary conditions at X equals 0 and X equal to L, but we have not taken care of what yet? There is something in our problem statement that has not been taken care of yet. The differential equation has been taken care of, right? The two boundary conditions have been taken care of. So what is missing? The initial conditions. Thank you. And let me see, what slide is that? 85. So let me jump for you to slide 87, assuming that's the correct slide. So this is the initial condition that we need to take care of, right? So u at x, at all x's at time 0 has to be equal to the function f of x that is given. So the only way to do this is to take a linear combination of the fundamental solutions to the problem, okay? So the idea here is it's linear algebra, really, right? We say this is sort of the basis, right, of basis elements of in my solution, or the basis elements. The actual solution is linear approximation, linear combination of the UNs. So the solution looks like this, and we want this expansion at x equal to 0, I'm sorry, at t equal to 0, where this exponential is equal to 1, to be equal to f of x. So when you do that, this is what you get. So can you tell me now what the coefficients in that linear combination of my eigenfunctions are going to be? Can we say something about the coefficient Cn? So when you look at this, can you say something about what these coefficients Cn are? That's a sine Fourier expansion. So can we say something about the coefficients Cn? You remember the Fourier equations? So what is Cn? Come on, where is my Cn? There is Cn, right? Okay? So I mean, at times t equal to 0, this becomes f of x, right? So the coefficient Cn will be given by this nice expansion. So we're done, right? So basically, what's the solution? I'm sorry, let me go back. What's the solution to the problem? The solution to the problem is this, where the coefficients Cn are given by that. That's the complete solution to the problem. So we have solved the differential equation, the boundary value problem, and the initial value problem for homogeneous conditions at the end with some arbitrary initial condition. And everything is given by a sine Fourier expansion with the coefficient Cn given by this nice equation. Okay? There is an example in the notes. I mean, nothing fancy. The initial condition here, I mean, this is a homogeneous problem otherwise. The initial condition is at time 0 is equal to 20. So 0 at the end, we start with a uniform temperature of 20 that obviously does not satisfy the boundary conditions, but the solution at any t greater than 0 needs to take care of that. And if you compute the coefficient Cn for the function f of x being equal to 20, you get this nice formula, all right? And the solution for this particular problem is given by this nice equation, okay? Okay, so, and the only thing, again, maybe I should emphasize this so we don't forget about it. This is very characteristic of this heat conduction or diffusion equation. you notice that there is an exponential decaying term there, e to the minus something of t. And that basically smooths the solution, because you can see the solution, you know, I mean, that thing approaches basically 0 as t goes to infinity. And this is what makes this series expansion to converge rapidly. You don't need a lot of terms, because if you put n equal to 5 here, this exponential is going to be so small that effectively its contribution to the series expansion will be equal to 0. Let me see if there is a picture to show you. So for example, if I ask you to plot the solution, you know, this is how the problem starts with a temperature equal to 20. Immediately, you have to take care of the boundary conditions, all right? And then as time passes, you can see how the solution changes. And eventually, basically, because the boundary conditions are at 0, eventually the temperature will be 0 everywhere, okay? I mean, the system will forget the initial conditions and will give you 0 solution everywhere. And that's another plot. So this gives you u as a function of x at different times. So if you want to plot now at a given x, the solution u as a function of time, this is what you see here, okay? So these are at different x's. You can see how the temperature changes with time. One way or another, you can plot things this way or that way. All right, so what I'm going to do is I'm going to jump now to slide 100. And before we had homogeneous boundary conditions, so the temperature at the end of the bar was 0. So now I want to change the temperature to be T1 and T2. Any trick, anybody that has in mind on how to solve this by using the previous solution? I mean, the only thing that I see that is different from before is instead of having 0, we have now T1 and T2. So can we use the previous solution and just add something to it to account for this problem? So let me give you a hint. How about if I define the steady state solution to the problem? And steady state means when there is no time dependence, basically, okay? Steady state, you will achieve it when t goes to infinity, but no time dependence, basically, in the way that I will define it here. So the steady state solution will have a ut equal to 0. And the differential equation effectively will be second derivative equal to 0. I call here the steady state solution V. And you know what? I'm going to put two boundary conditions to it. And those will be my two boundary conditions, T1 on the left and T2 on the right. Can you solve that problem? Can you compute the steady state solution for this problem? By the way, this is something you need to do in all problems, right? You know, if somebody asks you the steady state, you drop this, okay? And you put your boundary conditions, and you have to solve this equation with these two boundary conditions. So can you solve these two equations here? Can somebody tell me what the solution is? It will be a straight line from T1 to T2, okay? So and this is what we have. Everybody can see that? Straight line from T1 to T2. Now, I have to ask you again, all right, big deal. You got the steady state. My original problem is to solve the transient problem. How can I use the solution for the homogeneous boundary conditions, 0 boundary conditions, you remember, together with the steady state to solve my problem, where on the left I have T1, on the right I have T2. What do I need to do? Can I solve a modified homogeneous problem, and to that modified homogeneous problem simply add this solution and call that the final solution to the problem? So remember, this equation satisfies the differential equation. Okay? It satisfies the differential equation. It satisfies the two boundary conditions. But there's no time dependence, so it's not the solution to the real problem. So how do we modify the real problem so when we add this, it will give us the right solution? Tell me a new homogeneous problem that I can solve in a way that when that problem is solved and then I go and add this, I get the solution to the correct problem. Remember, right? The differential equations need to be satisfied, the boundary conditions need to be satisfied, the initial condition needs to be satisfied. So if I define a homogeneous problem and I put the initial temperatures to be 0, are my initial condition, the boundary condition 0, have I taken care of the boundary conditions by adding the two solutions? Because this tells me T1 and T2, so if the other homogeneous problem has 0 and 0, then I'm going to have 0 plus T1, 0 plus T2, right? Okay. Obviously, the differential equations will be satisfied, right? One satisfies, this thing here satisfies this equation, right? The derivatives with respect to T are 0, so the equation is taken care of. How about the initial condition? In my real problem, the initial condition is supposed to be f of x. So I need to solve a homogeneous problem so that when I add this solution, all right, I get the solution to my real problem. So I want to ask you, what initial conditions should I put in the homogeneous problem so when I add this solution, I get the right solution? My real problem has initial solution f of x. So I need to add the initial solution f of x, all right? So the initial solution is f of x. So I need to add this to some initial solution for the homogeneous problem. So my result is f of x. So what should I take as initial condition in the homogeneous problem? Will that work for you? I don't hear some. So what was that? Yes. So does it make sense what I'm going, right? So I am looking basically to add the steady state to a homogeneous problem, right, that I call here W, so I can get the real solution. And I say, if you look at the boundary conditions, V takes care of them. So I can put zeros on W, right? Zeros on W at the two ends. But the initial conditions need to be satisfied. Now this is something, V of x, all right? And so the initial conditions for W of x and t have to be f minus V of x. So when I add the two things together, when I add the initial condition on W with V of x, I get f of x, right? Okay, all right. You got that? So if you got that, this is the problem we need to solve. And this is exactly the same problem, the homogeneous problem we solved before. The only difference is instead of having initial condition f, now we have f minus V of x, where V is the steady state solution. And effectively, the solution for the homogeneous problem is identical to what we had before. The only difference is the coefficient C have to be computed for an initial condition, which is f minus my steady state solution. Everybody can see? Yes? Yes, all right. I'm going to put on the background some, recorded voices. Yes, 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 yes. Okay? So people, if anybody listens to these lectures, they don't think sort of I'm so wacko that I'm talking to myself and expecting a yes from a vacuum. All right, yes. All right, so we're done, okay? So the final solution to the problem is, this is the solution of the special homogeneous problem we solved, plus the solution of the steady state. And the only difference from before is the coefficients are given by this nice integral. So we have solved now the non-homogeneous problem, but with boundary conditions prescribed in terms of U. This is what we call essential boundary conditions were given in terms of U. And as lots of you know, when you take heat transfer, that's not the only reasonable boundary condition, right? What else can you have? Tell me fast because time is passing. What other boundary conditions except prescribed U you may have? Something with a gradient, you said, right? So you may have, come on. You may have boundary conditions given in terms of flux, right? So you don't want any heat in or out at x equals 0. You don't want any heat in or out at x equals 12. And you remember the flux is minus k times the gradient of temperature, but right now we do mathematics. So heat in and out, we write in terms of the derivatives of x, right? So those two derivatives have to be equal to 0. And so how do we solve this problem? Well, we do exactly the same thing, except the boundary conditions, instead of being specified U, will be the values of the derivative of U. So if you do that, and you do separation of variables, all right, you will come up with the same sort of problem as before. But now, however, you need to improvise and say, what type of lambda should I use? Because it doesn't work for all lambdas. And so let me just go rapidly. So this is for x. You have to solve this ordinary differential equation where the boundary conditions involve derivatives at 0 and L. So if lambda comes to be negative, all right, I am not going to do it. You will see that it doesn't work. You cannot solve this problem, okay? So lambda negative doesn't work, okay? And you can just follow the discussion. You basically get a 0 solution. If lambda equal to 0, actually it works, and you get a solution that is constant. It's not fun, but it's an important problem, right? The solution is not 0, it's a constant. So if lambda equal to 0, you get a solution that is constant. And the most important problem is if lambda is positive, and you set it equal to lambda equal to mu square, you can actually apply the boundary conditions, and you can see exactly as before that these eigenvalues lambda are n squared pi squared over L squared, okay? Exactly as before, there's nothing different. But now instead of getting a sine expansion, you're getting the eigenfunctions to be cosines. No big deal, okay? So basically, we have one eigenvalue that is 0, and it gives you a constant eigenvector. And then we have these eigenvalues, okay? And the eigenvectors are cosine. So the expansion is actually, so this is, by the way, how T will look like. And the expansion, so we'll have this eigenfunction for eigenvalue 0, and this UNs that I multiply Tn with Xn, which are cosines. And the general solution will look like this, all right? So the general solution effectively will be C0 over 2, right? Will be some constant term, plus this cosine Fourier expansion. And how do you get the coefficient Cn? Obviously, you have to apply the initial conditions. And once you say at t equal to 0, this is going to be 1, all right? And you have specified some initial conditions. You can compute the coefficient Cn's. And I don't know if the expansion is there. And we're done, okay? So that's how you take care of flux boundary conditions. Now, there is another boundary condition that's extremely important, right? These are the natural boundary conditions where you specify the flux in a wall that is proportional to the temperature difference. So those boundary conditions involve the flux and the temperature. So what you need to do is you need to do exactly the same calculations as we have done, and you will come back with some eigenfunctions and eigenvalues, put them together, you have a nice series expansion here for that case. There's a whole book. I forgot the author, but it's on my bookcase from the old ages. that basically the whole book is series expansions for heat conduction problems with every single type of boundary condition you can imagine, all right? And any single type of geometry. Karlslow and Jagger, actually, that's the book. And it's considered the Bible because those days, if you can get an analytical solution, you will put your name on the wall, somebody will put it on the wall. Right now, you know, somehow we're too lazy to come up with anything analytical, so we like a computer to do the job. And so, all right, so I'll see you on Friday, and don't ask me to tape this lecture again.